Okay, so one of the things we're going to look at is how to write half equations and then how to combine them to give you an overall equation. Half equations are really good for proving that oxidation and reduction has occurred because half equations need electrons to be balanced. And it is that electron transfer that is oxidation reduction. So if you see that an equation needs electrons to be balanced, you know that you've got oxidation or reduction. If the electrons are on the right hand side, it means they've been lost, so it's oxidation. If the electrons are on the left hand side of the equation or arrow, then they're being absorbed or gained, so it's reduction. Really easy way to explain. I know that such and such is being reduced because it gains electrons. I'm going to show you what I mean in this context here. This is an experiment you're going to do next week, if you haven't already. You're going to add acidified permanganate solution. I've put the potassium in there because it's a spectator ion. I want to talk to you about spectators. Acidified potassium permanganate solution, which means I've added some sulfuric acid to it. It's added to hydrogen peroxide, which is one of those really annoying chemicals because it can be oxidized and it can be reduced. So you need to look at the observations to know what's going on. If we do this, we notice that the purple colour of the potassium permanganate disappears. And we also, if we're observant enough, notice some small bubbles being given off. If I add the permanganate fast enough, it's really obvious. The bubbles are really obvious to see. So what we have to do is, the first thing we have to understand is what are the species involved. And for that we need to know that table. I can't remember the page, it's about page 56. There's a purple table. You need to know those pairs off by heart. The best way I could suggest to learn it is make flashcards with the oxidised version and the reduced version on opposite sides and their colours or observations. No Brain Too Small is a website and it's got those available for you for free. You just do a search for oxidation reduction, level 2 NCA, something like that, and it'll come up. So that's a nice easy way to learn it. I'm not going to put that table on our blog. It's there in your book, so I don't see the point in reproducing that. But do have a look at it in chapter 5. Okay, so when I look at this, I see that I've got a thing with MnO4 in it. It's also got a K. And if I look at my purple table, there's nothing there with a K in it. But I do see that I've got a thing called MnO4 negative, which is called permanganate. This means that this is what's reacting. The potassium's just there. It starts as a potassium ion. It'll end up as a potassium ion. If it hasn't changed, it's what we call a spectator ion. We don't include it in our equations. It's a spectator. It's not involved. But you can't just have permanganate ions on their own, so that's why it's KMnO4. It was made from crystals of KMnO4. They dissociate when they dissolve to K plus ions and MnO4 minus ions. These things are purple. Okay? So they're purple. They're what made it purple to start with. Okay? When it decolorizes, actually, I'm going to move the arrow over a bit so I know what's going to happen here. Our table on that page in chapter 5 says that it becomes Mn2+. What colour is Mn2+ according to that table? Colourless. That matches our observation. Decolorized. Colour gone. So I'm confident that this happens. Now the only reason that I can do that really quickly is because I know what we call the redox pairs. The oxidized version and the reduced version. And I know them off by heart. So I know that if hydrogen peroxide's reacting and this one's being reduced and if hydrogen peroxide's my other thing, I know it must be oxidized. So hydrogen peroxide I know can become water if it's reduced, or oxygen if it becomes oxidized. Not surprising when you listen to the names, is it? So at the same time, I must have this reaction occurring as well. I try to keep my arrows under each other because I'm going to end up putting everything together here to write an overall equation. Okay? So here I'm going to use these because they're great examples to go through the rules for balancing half equations, and then I'll go through the rule for putting them together. Hopefully it'll be concise. Slow me down if I'm too fast. The first thing I want to look at are whether the non-oxygens and non-hydrogen atoms are balanced. So if I look here, there's one manganese in permanganate, and there's one manganese in Mn2+. So tick, that's balanced. Okay, I'm going to give you quickly one that's not. If I had dichromate instead, becoming green chromium 3+, see how there's 2 there? I would need to put a big 2 in front of this one before I carry on. Okay, I'm going to wipe that one off because it's not related to this. But I check that other atom, so not oxygen or hydrogen yet. This one's only got hydrogens and oxygens, so I can't do step 1 on this one, and that's fine. My next step is to look how the oxygen's balanced, because that's, it's oxidation, so that's our step 2. Are the oxygens balanced? There's 4 here, and there's 0 here, so certainly not. So I need to add something over here which will balance those oxygens. But I don't really want to add oxygen gas, for example, because that's a product of another reaction. I need to have something there that isn't going to change what it is. Add water. Because this is a solution, I can add water. Because that doesn't change anything. There's water on this side and water on that side. We're just using it to help balance the equation. So I add water. 1 for each oxygen, so that's 4 H2Os there. Again, 2 oxygens, leave it. No water's required over there. Okay, I've now got those hydrogens introduced by water. 8 hydrogens have been introduced. I have to balance those out. The hint is in the very first word of what happened. It's acidified. Which ion do all acids produce? H+, perfect. So therefore, I can balance those hydrogens with the acidified bit. So I can add H+. And I actually add quite a lot of sulfuric acid to make the acidified permanganate solution. And this tells me why it's so much. There are 4 times 2, 8 hydrogens in there, so I need 8 there. This one doesn't have its hydrogens balanced, so what do you think I need to add on the right-hand side? 2 H+, brilliant. Okay. Now, for atoms, these are balanced. Okay? That should balance your atoms. It doesn't, however, balance your charges. If I look at this side here, I've got 1 negative and 8 positives. What does negative 1 plus 8 equal? 7. Cool. So at the moment, this side is plus 7. And this side has a plus 2, and what's the charge of water?
0.
Good. So it's just plus 2 over here. Electrons reduce how positive something is. So I need to get the bigger number down to the smaller number. So what I do is I add 5, I'm sorry this pen's not particularly flash, 5 electrons there, which will drop that to plus 2. And it's the same as that side. This is now a balanced half equation. The reason we can only call it a half equation is those electrons have to come from somewhere. So we need the other half of the electron, the other half, this one here, to tell us where they came from. In other words, they have to be a product of another half equation. You can't have electrons in a full equation. All right? Only in half equations. Okay, what's the charge on this side?
0.
What's the charge on this side?
2
Plus 2, not 2 minus, plus 2, but we are going to put 2 minuses in there, 2 electrons, to get it down to 0, because 0 is smaller than plus 2. So now you can see there's electrons on each side. Which one of these is being reduced? The giveaways on the side of the equation the electrons are on. Which one's having electrons added to it? So these are a reagent effectively, they're being added, so this is being reduced. Those electrons are allowing oxidation to occur, so we call this the oxidant, even though it's being reduced, because it allows the oxidation for this to happen. If it wasn't for this chemical, this one couldn't be reduced, so we call this one the reductant or reducing agent. But this process is oxidation and this process is reduction. And you know that by which side of the arrow the electrons are on. Okay? Okay, now putting them together is pretty tricky. especially with one like this, and I've chosen this one for the video because it is one of the harder ones. First of all, because you have to know which product the hydrogen peroxide is making, but also because 5 and 2 don't go into each other nice and tidily. You'd have to have 2.5 of this equation to have 5 electrons. You're not allowed to use halves. So it's really frustrating. So what we do instead is we multiply this one by 2, because of the 2 electrons there. We multiply this one by 5 because of the 5 electrons there. Whoops, sorry, I've done it lower. This one by 5 because of the 5 electrons there. We're finding its lowest common multiple, which is 10. We're trying to get both of them up to 10, because that's our, 10 can be divided by 5 and 10 can be divided by 2. So we've gone that way. Or if you like, I always just grabbed the number of electrons from the other one and did like a drop and swap type thing like I do with ionic equations. So I need to put that all together. So I've now got 2 MnO4s. I've now got 16 hydrogens. I've now not got 10 electrons, because 10 there and 10 there will cancel each other out. If you have something on the left and the right, you don't draw it at all. Just like we would have had a potassium there, K plus, and a K plus there, we haven't drawn it, so we don't draw the electrons. Okay? I've now got 5 H2O2. You can now see why I put the arrow so far over, I think. Then I've got 2 Mn2 plus. I've got 8 waters and 5 oxygens. Not quite done yet. This is bad because I've gone into there. Plus 10 H pluses. I'm not finished. Could anyone tell me why this is not quite finished? Not quite. The charges are good. This side is 16 minus 2 is 14. And this is 10 plus 4 is 14. So the charges are perfect. So if my charges are right, I'm good. Remember I said if something's on the left and the right, you don't write it. You get rid of it.
The hydrogen.
Good. There's 16 there and 10 there. So what I do is I get rid of those 10. And how many of these do I get rid of as well?
10.
10, so it makes it 6. Now I've got my final equation. 2 MnO4 minus plus 6H plus 5H2O2 goes to 2 Mn2 plus 8H2O plus 5O2. Alright? You could go through the process of checking every atom is balanced and so on. Please don't. You'll end up spending too much time on that. While you're learning it, fine. But in an assessment, don't go through that effort. So long as these are balanced, this will be as well. Okay, but please note, if you have hydrogens on both sides, then they need to be eliminated. If you have water, that's the other one that often happens, water on both sides, you have to eliminate from one side and reduce the other one down. Okay? So that's our half equations coming to an overall equation. Any questions before I stop this?